Awesome. Alright, I'm just gonna wait 10 minutes. Not 10, 5 minutes. And then see if everyone's here. And then I'll start. So, 5 minutes. It's okay if no one joins because they will just watch it later, hopefully. Oh yeah. Community Q fried chicken, okay. I will go tomorrow. Kimchi, right? Yeah. Okay, 9:55. Alright, question 1. Delta H reaction. Fairly simple. It's just products minus reactants. So we just go into products. So 2F2 is 2 times 0. CC4 is 934, or negative 100. And then minus the reactants, which is 2Cl2, which is 0. A CF4, which is negative 934. And then together you get 834. That's it. Very simple. Next, it's asking for which is not in the standard reference state. We know something's in the standard reference state if delta HF is 0. So the only one of these that is a non-zero delta HF is Br2. And a good way to think about this is that if it's 0, then that means, like, at rest, this molecule is perfectly happy being itself, right? It exists naturally. But for Br2, the delta H of, or the enthalpy of formation is a positive number, which means that it took energy to create this Br2, which means that it's a non-standard thing. If it was negative, then that means the formation of this is releasing energy. Yeah, so we're looking for the thing that has a delta HF of 0. And then this one's asking which one of the following statements best matches the data in the table above. That's, if you just look, there's a nice trend here where the heavier the molecule gets, the higher entropy it is. And you can see the trend by these numbers get bigger as these numbers get higher in terms of molecular mass, right? With chlorine having the largest one here, and then CCl4 having the largest entropy. That's just a good trend to see right there. Next is classic delta S. So pretty much we just use the formula here for this one, I think, which is product favored when T is above 1018K and reactant favored below, which means we know that something is product favored when delta G is, I believe, negative, yeah. So negative delta G means that it's going to be product favored, and a positive delta G tells us that it's going to be reactant favored. So we can tell that at this temperature, delta G is equal to 0. So it's 0 is equal to delta H minus T, which is 1018, delta S. And now we solve. Okay. It's in kilojoules because delta H is in kilojoules, so a simple conversion to joules turns it into this. That's it. Next is here. If 1 mole of solid Fe is produced by this reaction and 1 atmosphere, how much work does it do onto its surroundings? I think you're supposed to use a formula for this one as well. I'm blanking, sorry. I'm fairly sure you're just supposed to use the delta G reaction now. Yeah, I think that's what you're supposed to do. And I'm writing this as 0.1586 to keep units consistent. Hold up, wait a second. That is not the answer. Quickly look at the key because I am blinking. Oh, it doesn't tell us. How helpful. There's one where I did it with work. No. Hello. I'm blanking on how to do this problem. I think I'm getting a weird number. At first I thought I was supposed to use delta G to do it, but second. It's question B, part B. I think this formula is giving me the wrong answer, so I'm gonna quickly experiment with it a bit and then see. Well, this is good for me because I get to review it, but wait a second. I think I got it. Yeah, no, yeah, you're supposed to use NRT. Yeah, because it makes 1 mole of CO2 gas, which expands, and you use work is equal to this reaction there. And pressure is 1, delta V is unknown, N is 1, R and T are both given, delta V is like 98.47, and then work is 98. Negative, and I think the units for this one are in joules, I think. But I think my units are messed up. It's quite. What units this is in? Is it in? Oh, I know why. It's in liter atmosphere, so I have to convert to kilojoules. So this is. In order to convert to kilojoules, you multiply that by 0.1, which gets you 9.8 kilojoules. There we go. Okay, it took us a while, but we got it. This one, it's measure the heat released by the formation reaction for carbon monoxide. Blah blah blah. The water temperature increased by 52.8 upon forming 1 mole of carbon monoxide. What is the heat of formation of iron oxide? Okay, so pretty much we increase the water temperature by 52.8. So we find out how many joules of water did that take to raise it by that amount, and we have 500 grams. So we just multiply. So 4.184 times 500 times 52.8, and that gives us we used 110.46 kilojoules to form this carbon monoxide here. If you go up here, carbon monoxide is a product, and remember how this thing is products minus reactants. So we just do we just slap this and add it onto this value right here. So we add 110.46, and that gives us an answer extremely close to 272. And the reason why this is negative is because this is the heat of formation of iron oxide, which is a reactant. So it'd be this reaction backward. Alright, C. For this, just treat the delta G thingamabobber as the delta G reaction to, I believe, point slope formula. So negative T delta S plus delta H, where delta H is your intercept, and then T is your slope. So at T equals 0, delta H would be your y-intercept, which is this. And then you can just do a quick calculation to figure out where your what's its face? Your delta G is equal to 0 to find the T value. You plug in and you should get something like this. What's asking is value of the equilibrium constant K when T equals 298. Well, you can go back and look at this reaction here. Yeah, delta S, my bad. Oh, wow, I'm getting someone knocking on my door. One second. Alright, I'm back. The people in the suite across from us had their stuff stolen. I presume it was the 3 girls running around at 3 a.m. in my suite, so I told them what I know. Okay, back to doing this. Equilibrium constant when t equals 298. Just literally plug in 298 into this, or not plug in 298. First, plug 298 here to get delta G, then do the formula here. Delta G equals negative RT ln K. And then for this one, same thing. It's the same exact process. For this, asking for delta G, it gives us these partial pressures, which gives us a Q value. So same exact process, except do this, where this Q is based on the partial pressures of everything. So extremely simple, just plug in the formula, which is a recurring concept in this module, actually. Next is this. We can just mix and match based on this. So we know that Q1 has to be the aqueous form of whatever the cathode is here. So Cu2 plus, and then based on the value of Cu2 plus at 0.34, we can see overall E is E of cathode minus E of anode. So we have to find one where if we subtract from this, we will get this value, which is this right here. So we know Q2 and Q3 have to be some subset of iron, which is correct here. And then for this, it's asking for if we dilute both solutions. It stays the same purely because when we do these, both of these reactions are mono, not mono. Both of them have a charge of 2, where both of them are 2 plus, which means that they donate and take away the same amount of electrons, which means that their ratio should be equal. And because both of them have, E cell would stay the same. If the ratios were different, E cell would change based upon how the ratio of the electrons that your cathode and anode are producing. But in this case, they're the same, so you don't have to worry about it. Next, which molecule would you expect to have the most negative energy of formation? So all we do is we look and say, oh, which one would probably release, would release energy when it's being formed. So for this, we know N2 exists normally, we know O2 exists normally, and we also know methane exists normally. So I immediately just assumed it'd be this one because it's the only one that probably doesn't occur naturally or something, or is a rare version of the molecule. Also, it's heavier. So that's what I assume for this one. Because this would probably be 0, this would probably be 0, this would probably be close to 0, if not 0. Let me search that up, I'm curious now. Oh, well, that is fairly negative, but I guess if you throw in the oxygen in there, it becomes more negative, yeah, because of the weight. And then for this, upon adding 100 kilojoules of heat to a container of water, in order to drive this reaction forward, the final temperature of the system will be higher if... So this is pretty much... where is it? It's weird because you have to think about a container that you can keep pressure constant while increasing volume, or we keep volume constant but pressure changing. And I think this has to do with where is it? This one here, where it's entirely dependent on a change in volume, because we only care about external pressure and the change in volume, right? So here, what's a good explanation for this? How can I... Yeah. You have a box of the thingamajiggy, and if you heat the box and you keep, if you keep the constant pressure and the gas can expand, or the box can expand, right? so temperature would probably be fine. But if you had a constant volume and pressure increases, then your little molecules inside are going to be able to move around a lot. There's going to be a lot more collisions. So it's probably going to raise the temperature, right? But if you think of the other one, where your volume can increase, it can keep the pressure constant, which will keep like the energy of the whole thing, I guess, the same. So temperature will stay like somewhat the same. I think that's it. Yeah. And then for this, it's just I believe you use the delta G with the E reaction, which is this one here. You just plug in to get your answer. Yeah. And then Y is Gibbs free energy, a useful integration of thermodynamic properties. Okay, I know the answer key does a much better job explaining this than I do, I think. If I go all the way down. Where is it? Here. So, pretty much, it keeps track. Well, yes, delta G won't tell us whether or not a reaction is endothermic purely because that's entirely based on your delta S value as well, right? So if delta G is positive or negative, we're not sure because depending on the size and magnitude of temperature or whatever, we're not 100% sure on whether or not it's exothermic. Same thing for vapor pressure. It's like general, so it's not really telling you what vapor pressure is. You can technically get to a K or a Q value, but it won't really get you all the way to vapor pressure. It will just get you to K or Q. And then for this, it's for the Gibbs free energy thingy, we don't have to calculate delta S. I'm not entirely sure. Just read it for this, but I just assume know that you can calculate entropy off of delta G. Alright, I think that's it for the practice. So we go to the actual. And the actual is pretty much more of the same, which is, wait, this is multiple choice. All the way back to here. So if you look which reaction requires the least amount of heat, just look for something that what's its face, has like their overall delta H has, I think, the greatest value. So I think you just do the math here where you say, oh, SiO2, so this entire thing would be positive 910, right? Because it's products minus reactants, because Si solid and O2 gas are in their standard states. And then for carbon monoxide, you do 2 times negative 110 minus minus negative 910, so that'd be close to like 700 something, right? And for this same exact process, so this is going to be most negative, or the smallest delta H value, so it's going to be reaction 3. And then in which reaction is Si reduced? All of them. It's literally gaining an electron, right? So if you look, SiO2 is -2, right? And all of them have an oxygen attached to it, and then they go to their standard states here, which is 1 without a charge. So it goes from being Si, I think, 4 plus to offset the 2 oxygens of a -2 charge. So it gains 4 electrons as it goes across. So all of them are reduced. And for this one, if it has, for reaction 1, which is this, just pretty much use your delta HF and figure it out from there, where you can probably assume that because it's going from standard states, or going from something to its standard states, and also that it's breaking apart into 2 different things, you're probably going to have a positive delta S value, I believe. Yeah, so it's going to have a negative slope, and your delta H of that reaction is already positive, so you start positive, go negative. And for this, it's just plug in to your reaction here. So when it's asking for switching from reactant favor to product favor, we know delta G is 0, so just solve for temperature. And for this, it's just convert, or just plug in these values, so 298 to 1970, find the difference, and then multiply that into here with the 0.3 as well. They give us a melting point to throw us off here. This is melting point in Celsius and not Kelvin. If we convert it to Kelvin, it'd be 1973, which is extremely close, but it doesn't pass the melting point, so we don't have to like factor in the melting point into our calculation at all, so we don't have to worry about that. Next, we have delta G. So pretty much based off the KSP, we can plug into negative RTL and K, and we get this value, which is a positive number. And then it gives us concentration of PV and BR. We just do negative G RTL and Q, where we do the Q expression, which is products over reactants, except the reactant is a solid, so we can ignore it and only use the products. Plug in here and solve for delta G, and that gives us this number. For this, it's asking for delta H, so pretty much we know delta G off of the previous question, so just plug in and solve for delta H. For this, it's if we didn't know delta S reaction and we wanted to solve, we would need delta G reaction, because delta G, you can use it to cancel out, I guess, the delta H's across both, because delta H will be consistent across both of them, right? So you can set them equal to each other, where it's T1 delta S minus T2 delta S, right? To find delta H. Because it's just like a system of equations where you have two different reference points, I guess, to solve. Because although our delta G's will be different, the delta H's across both of them will be the same. Yeah, you can use that to solve for delta S. Next, this is pretty much the same thing that we went over earlier, so I'm not really going to explain these three because they're the same. We know that the anode will always lose mass, right? Because it's losing electrons, so it's going to lose mass, while the cathode will gain mass. The cathode's electrode will gain mass, right? And then for maximum amount of work this can do, if all species are at standard state, we literally just do delta G minus RTL and K, and then just solve, and that should get us that number. And then for this one, it's asking how it would happen if one solution was increased while the other stays the same. So for that, we just look at how it would affect our, I guess, concentrations of this and this, right? So if Cu's concentration is increased while the other one stays the same, our Q value increases, right? Well, not Q value, wait, hold up. We literally just have more the anode, and when we're adding it's cathode minus anode, right? So if we have more anode, then it's gonna become more negative, right? Because we're subtracting. No, hold up, am I tripping? Wait, I can't scroll up to look at the formula, but I can look at the formula from here because it's the same formula sheet. Yeah, so pretty much your Q is going to end up changing, and based off of how that works from here, your number is going to get smaller. Next. So for this, it's asking use enthalpy changes. So literally just see how they add up together, I guess. So, I think it's literally just you flip this one around and then add the two together. So I think it would be 312 plus 0.9 plus negative 91.2, which is 221.7, yeah. And then how many have a delta S that's greater than 0? Well, if you look at these reactions, it goes from 4 moles of gas to 2 moles of gas, 3 moles of gas to 2 moles of gas, and then 2 moles of gas to 1 mole of gas. So all of them are a negative delta S. For this, it's asking for which of the reactions are exothermic. So if you think of combustion of gasoline, it literally powers an engine, or not an engine? Yeah, an engine off of its energy, right? The energy it produces from the gasoline's combustion reaction is used to move the pistons and how engines work. And then when water condenses, it's switching states from gas to liquid. And because it's going down in its energy state, it's releasing energy. And then it's the reverse here. It goes from solid to gas. So it's obviously not, because delta H is bonds broken minus bonds formed, right? And from going from solids to gas, you are breaking a lot of bonds. So delta H is going to end up being positive, and same thing for this one. And then which of the following have delta HF equal to 0? Just look for something in its standard states. Cl2 gas exists naturally. Nitrogen, this is nitrogen as a liquid, which is not normal. This is hydrogen gas, this exists. And this is this is chlorine on its own, which is not normal. Chlorine gas is always diatomic, so this is also not normal, so it's A and C. Also, why did my music stop? Yes, I'm still watching. And then for this, it's saying, which of the following is a system of entropy change negative? So if we think, oh, we're evaporating alcohol, so it's going from liquid to gas, which is probably a positive entropy state. Or burning paper, it goes from solid to it's breaking apart, right? So this is also that. If we are heating, this is pretty much the question where it's asking about constant pressure versus constant volume, right? So if we're compressing a gas, we are decreasing like the entropy, because if we think about it conceptually, entropy is like randomness. And you can't really have a lot of randomness if the amount of space you have available goes down. While if you heat it, all it does is just, it makes it go faster. It doesn't really do anything. So what we really care about is the change in volume rather than change in temperature. Or not change in temperature, constant pressure, sorry. And then an unsaturated solution of a mystery salt, blah, blah, blah. You add a little and see that it disappears. And the temperature increases. Which of the following is definitely not positive? Okay, so we know that off of this, delta S is definitely going to be a negative number, because it goes from being a solid to it goes from being a solid to aqueous, so it's gonna become more random, I guess. So because a solid can't really be random, yeah, like in its positioning, but if you break it apart and put it in water and let it float around, it can be more random, which is what I thought of when I was doing this. Or not delta G, sorry. Wait, yeah, if you think of delta G, sorry, I literally thought this was S and I like made up a little answer that was completely wrong. But for delta G, we know that it's negative because I think it's because this reaction happens spontaneously. Do we have to do anything to it? I think, yeah, negative delta G means that it's spontaneous. It favors products. Yeah, so if it dissolved on its own and we didn't have to do anything with it, then we definitely know that it was negative. Yeah, for delta S, we don't actually know. That's my bad. Same thing for this one. Um, if we do the exact reaction with a moving piston that's free to expand, if the delta V, if delta V can change, you are going to have like less temperature, like more of the energy is going to be spent in moving the volume than it is in raising the temperature. So the one with the piston would be at a lower temperature because some of that like energy that we spent in burning methane is going to have been spent in actually moving that piston instead of heating the methane. So we care more about the box. Is that it? That's it. Oh, okay. Thanks for watching, I guess. That was really fast. I feel like that was like at least half the time it took compared to the other ones. But again, the other modules are older and therefore harder. Okay, I will see you all tomorrow, hopefully for module 4, if I can speedrun learning it in that time.